So, good afternoon. Sorry for the wait, but some trouble in the compilation. First of all, the date of the exam is fixed. I was a bit late, but it's now 5th of September at 1 o'clock. It's 19 minutes, 90, and it's a clausura because we are not people. Many people are attending, but the number of people listening is quite high, so that's why this will be written. So I hope that is okay. It's just like can't be otherwise. So that's the announcement, and you can now sign in as requested, because some of you might have had a problem doing that, but it's not possible. Okay, what we are going to do today is, this is really a nice lecture today. It's to explain what are really special things about RF devices. So this is really the core of this lecture today, to explain why we have such a nice overview of devices, and to understand why we need certain features of the devices which will be used in the everyday's life. And what you learn today is directly connected to the lifetime of this, to the capability to use something at any frequency, and it's really the baseline why RF is specific. So that's what we last time heard already. There was a small repetition that is just like that there's always a connection to the crystal when we're talking about properties, but it's not about fundamental physics, but it's about the idea that things have to be better for us in terms of turning microwave efficiency into something useful for you. So we have most of the devices we have today, they are always limited. We are exploding in bandwidth, and even if we can today do very well these frequencies, so up to 3 gigahertz, that works pretty well, as you know. You can run around with that, but the requirements always are we need better devices, because we always have such a frequency that it's not good enough. So we have to make new choices of materials and so on just to get that right. Yeah? Typically, we say that the separation between insulator and semiconductor is at around the band gap of 4 eV. And why to mention that? That is just this idea that you know what a metal is, you know what a semiconductor is, you know what an insulator is, but why to go to these specific frontiers? And that's something we already looked at. Just see, this is this idea. When you have when you're comparing materials, and we are always advancing materials. So, for example, when we are today discussing 5G and 6G, is only possible because we are taking the latest advances in material science. So if you want to say you want maybe, when we started this, it was maybe 10 megabit per second on the cell phone seemed extremely high. Today it's very normal for you to download at this speed, and we will soon see maybe a gigabit to the cell phone, and not just over Wi-Fi, as you might be able to do today already, but also over the normal mobile communication. So we need devices where we are high in these criteria, where the mobility, which we said is a measure for current. Yeah, so mobility is proportional to the current because it's essentially Ohm's law, as we said. And the other one is the voltage capability, which is in this case represented by the band gap. Yeah, so we want to research materials which are somewhere here to be useful for what we are doing for conversion in efficient devices. This is true for switching, yeah, so for power devices. So this is not just me here standing with my cell phone. This is a fundamental idea. Yeah? And how do we look at that? So we have, when we have just to say it from the very simple transport, you say you have a crystal, which is a bulk, and you say that you can contact this with idolized contact, which is not typically true, but let's assume that. Then we put some relations between voltage and current. And then we have selection of devices in band energy. So we have silicon as a reference, 1.1 eV. we have germanium, which is already used quite nicely. So the silicon chip, which you're using today for the memory, as we learned, is not just a silicon chip, it's a silicon germanium MOSFET. Only because of that we can make good devices, because we reduce the band gap and we win in mobility by that. The other thing is we use different devices than silicon, and that's particularly for the mobile communication for the 5G. The material you use on this side is, because it's battery driven, it's gallium arsenide, which is 1.4 eV, but it's much better mobility, so you make use of this advantage here. Yeah? And on the base station you're talking to, you're looking at gallium nitride, which is the reverse, and this needs a higher voltage because it's higher power. But you see already on this world map, you see you're always using the latest advancements. Yeah? And there's also a very practical reason for doing this. So this sounds like basic semiconductor physics, but it's money in your pocket, because there's so much of this thing you pay for this is energy. Yeah, so 20% of what you pay for mobile services is simply energy. Yeah? So anything which helps to avoid converting electric current into heat and turns it into microwaves, this helps you, because you're not paying so much anymore for these services. And we are continuing to work that up. And let's now discuss what is relevant. Yeah? So getting a bit back to more physics. So what is the mobility? This is this idea that the carriers are drifting at a certain speed, and the mobility is essentially the drift velocity over the E field. Yeah, so if you write that in a different way, then you could say the E field is the drift velocity by the mobility. So you say that this is essentially an ohmic assumption that 1 over the mobility is the resistance, and the drift velocity is a measure also maybe of the current flow. So that's one idea. But the critical idea which comes from this is another one, because in semiconductors we are not necessarily having the carriers. So in a metal, it's very clear that we have 3 carriers available. We have enough carriers, 10 to the 23 cubic centimeters, they are available. But it's not true for semiconductors, because semiconductors can be extremely well conducting, but they simply don't have, they're simply not there. Yeah? And that is why we make such a fuss about the semiconductors, because you see here that the Fermi level, the carriers available, are not touching the conduction band. Which means that we have potentially a very nice motorway in this idea, but we don't have cars on it. And this is something we are going to discuss today. The second limit is, so first of all, what is the carrier limitation? And we are not doping. That is something, so when we are at finite temperatures, this is something which is not often clearly stated. So I told you at 0 temperature, the mobility of a carrier is essentially ideal, because you don't have any reflections because of the phonons. So when I'm accelerating by an electron into the crystal, there's nothing swinging, so the path of the electron is quite nice. And also the impurity, which is the second disturbance, so to say, in this crystal, is also not there if it's a pure semiconductor. The trouble is when you then check what you get just by the basic concentration. So you have a basic law which says that the concentration of N and P, so of electrons and holes, is an intrinsic concentration of carriers to the square, and that is bound to the band gap and the Boltzmann constant, which is here Kb times T, and at room temperature this is 26 millielectron volt versus a band gap of 1 eV. So this term is relatively small. So this is an exponent which is high, so the overall term is relatively small. So there is very little concentration when we are not doping in the carrier. So you have now built with this, with an ideal semiconductor, you have built a road where you have a good transportation, but the carriers need to be close here to the conduction band with a limited separation. And as you see here in this, if this is silicon and you are in the middle of the band, you simply have no way to transport carriers because they wouldn't statistically go to the conduction band. So that's one limit. The other limit is, of course, there's also a potential that we can increase the voltage to get more transport. And there's the simple idea that you have a maximum field. So ideally, it's a linear relation between the voltage and a critical field. So you could say that there's simply, first of all, a voltage limitation. And if you look at this from the critical field perspective, this is okay. But typically, the fields are lower than what you get as a critical field. So the devices break as when you put voltage to them at fields and voltage is lower than the critical fields would say. Typically it's 1/10. Yeah? So if you have for the critical field idea, then typically this is much lower. And the reason is that we have very strong gradients in this field, because all these considerations for a critical field are always based on the idea that this is a very homogeneous crystal, but that's not true in process devices which have doping profiles, for example. So what you get is a voltage limitation. We'll talk a little bit about that. Is lower. Yeah. So that also, so there's a current limitation and a voltage limitation, which are both given. Now coming to the what can you do? Now we are putting cars on the road, and there's two ways of doing that. In silicon, very nicely, you can put a donor level by doping a group 3 semiconductor into the, group 5 semiconductor into group 4 silicon, and then you would have additional donors, so that this intrinsic concentration of carriers is added to. You have more carriers, and the same works in the same way, especially for silicon, that you go to an acceptor level. So what you say is you put holes, which is a group 3 semiconductor, into this crystal, and you disturb the crystal, which is nice because you get additional carriers in electrons and holes. The trouble is that, remember what we assumed here, that the crystal should ideally be not disturbed, but if you're putting a different ball, so to say, to the crystal, then you're disturbing this regular shape, and that also reduces the mobility. So with every carrier you put to the crystal, you're reducing the quality of the motorway. These are the two effects. Yeah. So impurity doping does that, and also temperature does that, and that is important now. So as we all want to organize traffic, the idea is we have to get more carriers into the crystal, and the easiest way is to dope. But because intrinsically, this is what I said earlier, you have a thermal excitation, which is this exponent for the intrinsic concentration of the carriers, that's around 20 millivolt versus maybe in silicon 1.1 eV. And if you put that on an exponential function, you get a very relatively low thermal excitation. And then you start to implant, for example, to put carriers. But that's not the only way. Most of the semiconductors have also a natural background doping. So it's very unusual to have this idea that you just say the crystal is perfect. Most of the carriers ground are also in there because of the environment, because they're put traps in the crystal, or there's also some unclean conditions, so which in the end lead to the fact that there's always some co-doping. So this is not, it's only for silicon that we have such a nice situation that we get a very clean signal crystal also. Yeah? And now we have to organize traffic. So that is number of carriers versus good motorways. And what is the relation? And this is now a very fundamental plot for silicon, and it's very critical. So we are at a very specific temperature of room temperature, which is good for us. Our cells work well at 300 K, that's what they're made for. If we were thinking from a transport perspective, we would probably want to be at a different temperature. So for semiconductors, the conditions for current are better at lower temperature. So you see that here plotted, which is the mobility versus the temperature of the crystal. And you see at lower temperatures, the mobility is enhanced critically. We have to be a bit careful because that looks like it's an exponential behavior here, but when you're going to too low temperatures, also the mobility drops again, so it's a maximum somewhere. Yeah? Here you see around, so when it's very cool, the carriers are, the mobility is better, and for some electronics we even make use of that. So there is, for example, if you're working for the radio telescopes, they cool this stuff down to the very low temperatures just to have better transport for some amplifiers. So this is not just physics or some crazy professor talking about stuff. This is reality, that you really want to enhance the receiver, for example, to make use of better mobility. So you don't do this, of course, with this, because cooling this would be too inefficient, but it's this is a real reality. The second point is that you have a strong dependence also, and that is very temperature dependent. That's why I plotted this way, that the impurities hit much stronger relatively at lower temperature. So you see when you go down to a nearly an ideal crystal and it's not doped, and you're increasing the doping that from mobilities in the order of 10 to the 5 and higher, you go down here to 10 to the 3. So typically we say silicon has 1400 in mobility and then reduces with the doping. You see it, there's a drastic change also here. And this is what I said earlier. Once you start to pollute the crystal, the phonon bouncing, which is banging my head because you're hit, or also the impurity doping, both hit. And you see this is an exponential behavior over temperature and also over doping. Yeah, so that shows you that the crystal gets worse. The trouble is, a motorway without carriers is useless. I mean, that's also very obvious. If you simply don't have anybody to travel, then you don't need to build a motorway. That's very clear. Yeah? Now, what can we do? And if you were just in this bulk weld, then things were very simple, because you see at room temperature, and this is where we are at, there's a relative impact of the impurity doping. So this is when you increase the concentration, the mobility goes down, but the strongest function is also the temperature, because you see how from, let's say, from 10 Kelvin to 300 Kelvin, you see there's orders of magnitude in loss in performance. Yeah? Let's review a bit how current works, because we are typically missing one point. So we have in our heads very clearly that voltages activate current. This is based on our thinking from Ohm's law, and it's correct that the carrier density here given for both electrons and holes, that this is a function of the voltage, so that's the E field. Yeah? So the current is proportional to the voltage, which is somehow good. Yeah? So here is what we have in the intrinsic mobility, and you see also here, this is what I'm talking about all the time. You need the additional carrier concentration, because only if cars travel, then there's traffic. So this is this equation which I'm constantly talking about. Yeah? And the thing what we talked about so far is that if you are getting this up, you are losing this. So this product is somehow constant. So this is what we get from the material. Yeah? The second contribution, however, is even more important. And this is this idea that we have in a couple of ideas already. It's the diffusion current, so that it's not only activated, current is not only activated by voltage, but current is also activated by carrier gradients. And I'm always missing that myself, and it's a very fundamental effect, and it's critical. It's critical because this effect makes some devices much better than others. Yeah. What is this about? This is the, let's see whether I have this. No, I don't have the plot, but you know that that's the fish tank. You have a glass or an aquarium of water. You put a bottle of ink on the right side, and half an hour later, the whole aquarium is blue. That's something you've seen before. It's a very fundamental effect in nature, which says that there's always a movement of particles against the carrier concentration gradient. Yeah, and that's this. So if you have a gradient in the carrier concentration, that alone causes a current, and that's vital. That's defined by a material constant, which is here this D, and as you know, the fish tank is getting blue. It's summer, so you might have seen that in recent times, and it's important because where would we have carrier density changes? And for example, I would like to remind you that when we, for example, in a MOSFET, which is indicated here, you need the contacts. Yeah, so just to get the current in, and one way of doing that, this is often missed when we start the process. So here we said we have an ideal semiconductor, and you just put the metal, but typically if you just put metal to the semiconductor, that does not make a good contact. Yeah? What you typically have to do, we will come to that, is that you add a high number of carriers under the metal just to make it an ohmic contact to transport into the semiconductor, which means if you need a different concentration elsewhere, for example, here in this MOSFET area, then you have a carrier gradient. And this alone, without any voltage, will cause a current flow. And the same idea is also true because we are not only discussing one carrier type, but two. And also this is important because we have two measures of carriers which influence each other. So carriers and holes interact, but first of all, they are independent sources for current to flow. So you can get a second runway of carriers in the same material, which is nice. So you get the same material, and especially for silicon, this is another advantage of silicon. The current conduction of electrons and holes is about the same, not just identical. But the mobility in silicon for holes is only a third of the electrons' mobility, while in other semiconductors, the P conduction is much worse. So for example, in gallium arsenide is pretty much reduced, while in silicon it's good. So silicon has another advantage of having both carrier types available. Okay, so that's, having said that, we are in good shape. And now, how do we get better? So when this is everything, we can make now some devices, but that's a bit short-driven because if we did this, we couldn't make the devices we want to do because then we would essentially be stuck to the materials which we have. So we can organize conduction, we dope, play with the principles, but there is a problem because when we want to improve things, and for example, the good revelation when people hit the ceilings was the developments of good microprocessors, because what people learned was that if we didn't improve the mobility of the materials, then you would start to have some other issues. For example, what would you say is the limit of present microprocessors? What is your feeling about that? What is mainly limiting when we have them in PCs, for example? Any ideas? What would limit them? Or also in the microprocessors, and what is our interest in these devices? So we made them better, and at some point we'll get running into some trouble. So Moore's law was saying we're putting more and more devices to a small area, but what goes wrong then at some point? For example, if I do this, what do I feel? 70 degrees. Yeah. So this thing is really hot. I'm always worried in summer. And so you say you can do all these nice changes to the organized conduction, get it nice, but already with this, you're simply producing too much heat per area, which is equivalent to the mobility problem, because simply, you know, for example, when you today buy a high performance processor, you buy a quad core. And this is already telling you something, because if you look at that chip, yeah, apparently for thermal reasons, they make the individual chips smaller, but they put 4 of them a bit adjacent, so they don't keep them stuck together, but they will make the processor architecture bigger and put them individual, because they need the spreading of the heat to keep it at reasonable temperature. Yeah? And it's telling, because this has nothing to do with RF yet. So this is just what you just use. So if you're typing, this is exactly what you use. But there's some relation to RF. For example, the CMOS chip, I mean, 22 nanometers by now is a bit boring. The reason I'm talking about this is that it depicts a frequency of clocking. And the clocking frequency of those switches is just about it's 3 gigahertz and 3.9 gigahertz, which is exactly what we're using with our new 5G chips. So the new bands in Germany, when we were discussing, so up to 4G, everything was up to 2.7 gigahertz, 2.8, and now we're using these new bands 3.4 to 3.8. So it's exactly the same frequency, although it's clocking, it's not microwaves. Yeah? But we start to think, yeah, there's a relation. Yeah? And the idea is now, what other features do we have to think about? And the solution and also the effects we are taking to reduce the heat in the microprocessor, which is the same as increasing the efficiency of a microwave amplifier, is to say, let's look at the effects of small devices. Yeah? And some effects we have to observe anyway, because we are running into limits. And one limit is, what I'm depicting here is the gate of the CMOS, which we are using. The node is 22 nanometers. And when you are a bit into physics, you start scratching your head when you hear that number. So it's very good, of course, because we can put all those billions of transistors on the Intel chip, which is nice because we get more function. But there's also a fundamental problem which we are hitting. So the present CMOS devices, the complementary MOS or the MOSFETs, which I think you know what a MOSFET does. However, there are no real MOSFETs anymore. There are MOSFETs, but they are very specifically modified already. Yeah? And the reason is that, you know, that 22 nanometers for memory is outdated, completely outdated. Yeah? So 22 nanometers maybe was 2008, 2009. Yeah, so that's 15 years back. And the reason what we have to think about is that when you play with the dimensions of a FET, everything gets smaller in length, so the gate length of the FET, so the distance between contacts, but also to get the control, the thicknesses of the oxide are getting in the ranges of a few nanometers or even a few atoms. And then things start to be a little bit critical, because when you go into this regime, the laws of solid states are modified by the quantum laws. And how can I see that? That's quite simple, because in your physics career, you might have heard this big story that the physicists always were talking, particles are also waves. Yeah? And that some physics teacher told you that, but for the electronics you're using, this has dramatic consequences. So, and it has good consequences, by the way. How can I see what's happening? You know that the guiding equation for the quantum part, so the quantum effects, is the Schrödinger equation, which is an equation which just happens to be valid. But in a way, it's a wave equation. That's the sound idea. And without having too much trouble with this complex differential equation, one thing you always should do when you're looking at differential equation are the guiding quantities. So which numbers define actually the scale? Yeah? And for the Schrödinger equation, there's one principle which pops out, that the wave function is a wave function, so it must have a wavelength. So the electron is a wave. And now you can perfectly relax and say, okay, let's find the equation for the what that is. And then we're getting back to something which is relatively predictable. So there's the h in there, which is the constant. There's the effective mass and the Boltzmann constant again, times temperature. And if we do that, we just multiply these numbers, we are getting that for gallium arsenide or silicon, we are just about in the range of 20 nanometers. Why is that interesting? Because we just said the quad core has a gate of 22 nanometers. It's not the physical size of the node, we have to be a bit careful, but roughly it's 22 nanometers. And then I ask you, what is happening if in any wave equation which you have encountered in your life, if you are hitting the wavelength with what you are doing, what is then typically happening? Yeah, it's a kind of resonance. That's interesting, yeah. So in optics, you know that, and especially, but resonance is correct, but it also means that from there, things change. If the wavelength of the object is getting smaller than the environments, then we are a bit in trouble, because then we are definitely in the range where different laws govern. Yeah, and I want to point out one fact. We have this very strange idea about a gate. Yeah, and when the electron behaves as a wave, then something very fundamental starts to be tricky. So we have that strange idea that there's a source, a drain, controlled by a gate. Yeah? So you have that idea, you learned that field effect, modulation of the gate controls the current between source and drain. That's a MOSFET. The trouble is, this effect starts to vanish the moment when you are going in the direction, or to be precise, on the size of this wavelength. Yeah. So if the object which you're seeing is smaller than the wavelength, then suddenly this idea that you control the source to drain current by the gate doesn't work anymore, because the electron traveling from source to drain simply doesn't see the gate anymore. And now you could say, why am I interested? And I say, you are very interested, because let's remember, if we are these guys, what is the limit? The limit of this is the leakage. Yeah? Because the beauty of this device is that essentially it is not consuming any power. It's only consuming power if we are dynamically operating it. But the idea of a switch is that it's critically on with low resistance, but also very off. So a switch means you open the door and you can close it. The laws of physics tell you that the current flow between source and drain at a certain size of the structure starts to be limited. And it has a very concrete consequence that you get leakages. Yeah? So you have to think how to build a good MOSFET even under these sizes. It's possible, apparently, because if you have any modern iPhone or whatever, you're using 3 or 7 nanometer chips. So apparently there's a solution. So the MOSFET is not abundant. But you have to think, you make a 3D MOSFET, essentially. You have to think about a lot of additional things. But that's something which can be done, but it's not so easy anymore. The second idea is you have this idea that a MOSFET, that's what you learned from the beginning on, the MOSFET does not have a DC current because there's an oxide between the gate and the semiconductor. In my PowerPoint engineering, that sounds like to be about right, because you have something in this block oxide, you have a material which obviously is not conducting. But we have to step a little bit back and think for the following reason. A MOSFET is only good if the control of this, or the flow of the electrons, is near the gate. Yeah? Because, for example, if it's like in this room, if I'm trying to control somebody on the last seat of this room, if I'm having somebody here, I can influence them. If she or she is up there, it's difficult. Yeah? And the same principle, and maybe I give you also even a number, it's about 10 to 1. So when you have 20 nanometer gate length, you typically need an oxide in the range of 2 nanometers to get good control of this on-off. Yeah? If people are far away, then things are getting lousy. You can measure that also, I can explain that later, but just as an idea. So that means this oxide is about 2 nanometers or less than 2 nanometers thick. How many layers of atom is this, a nanometer? I think you could be able to know that. So what is the, of a reasonable atom, what is the size? If you now think in balls again and not in waves, what would you say, roughly? What is the unit of atoms? It's angstroms, or 10 to the minus 10, and we talk already for the gate length, we talk nanometers, so that's 10 to the minus 9. So any atom is a couple of angstroms. So you might have, for the oxide, you might have 2, 3, 4 atoms which are representing this oxide. Yeah? This is a technological problem, but even if you can make a perfect oxide, which we, by the way, get from silicon dioxide, then the idea is simply this is too small in relation to the wavelength. So already into the gate we have a problem, because the wave can go to the gate metal without seeing the oxide. And again, what is the fundamental problem of the wave not seeing the oxide? What problem do you get then? So if you have an oxide or some cable which has a very thin wall and the wave goes through, what will happen then? Just from your, what would you say? Something gets very thin, then what is this effect?
You would lose the controllability of that device.
Yeah, but it's even stronger. It's even like in the in some other effects in waves. We call that tunneling, because if the object which is inhibiting the wave is much smaller than the wave, it just goes. The wave just passes, and it tunnels. Yeah, so it can actually go through that gate, into that gate, without seeing it, which is again a problem, because in the processors, remember that these work so nicely because the MOSFET simply doesn't have any DC current to the gate. Yeah, that's one of the nice ideas. So also we lose that. Now, so this is this tunneling. So when we just take a planar MOSFET, we lose controllability and we get leakages. So we need to think about both. Yeah? And I'm just mentioning this because anything we are doing now is already in the scale of quantum mechanics without having much problems with that. But the idea is, because we have this, we want these high frequencies and we want to follow up Moore's law, which says more devices to a small area, so everything gets very small. That is a challenge. Now, and what I would like to mention again, this is not something which is an imperfection in terms of technology. Tunneling is something which happens just because of the size effect. Yeah? So that's the governing principle for, so for example, a MOSFET is not blocking because of this tunneling. Yeah. Before now we go to the small stuff, we also have to think a little bit about what we want in RF, because we now came to these very small regions, which means that we will have a higher limit for the voltage. Yeah? So ideally, when you just think very simply, a MOSFET has two, or any transistor has two regions, a linear region and a saturated region. The upper limit for the saturated region, when the carriers are just traveling, is a breakdown. And why does a breakdown occur? This is something where we look at it occurs not only in MOSFETs, or not only it occurs essentially in any device, but it's a high field effect, and that's something which we have depicted here. So when we have when we look at the velocity, first of all, of the carriers going under a gate, then you see that they are very pronounced at the edges. Yeah, so it's not only this limit which I was talking about earlier. It's not just the breakdown field of the nitrides or of the oxides which are around the device. It is very much in the channel. Yeah, because when we look at that, when we look at the composure maybe of a MOSFET, which we'll explain in a minute again, you see that even for relatively large MOSFETs, the maximum velocity of these electrons happens here at the drain side of the gate. Yeah? Because the electrons get the maximum energy when they're accelerated exactly there. And this is particularly not only because of the acceleration between source and drain, but also because there's a doping profile change. Yeah? So especially these changes in the doping profile create very high fields. So it's local. Yeah? So the oxide, apart from starting leaky because it's getting small, this is combined with the electric field focusing at some point. And so it's not that when you have this idea here for the oxide, you could argue that it's just thin, but it's very balanced. But it's not true, because we accelerate the carriers under the gate, we also hit them locally into very high speeds, you could say that, or because we're creating doping profiles which cause the field to be relatively focused, you could say. So what we get overall is that there are regions in the transistor, or later on also in the bipolar, which are particularly affected by hot carriers, accelerated nicely. So you see the drift velocity in normal is just maybe 1 × 10⁷, but here they are really turned into high energy states. Yeah? And that's what really limits devices when they're getting small. Yeah? Because we are pronouncing these doping gradients to make the devices more efficient, but at the same time we're also creating a large number of problems, and you see that they're and it's not for something which is particularly small. You see the scale there. This is even for 150 nanometer or 180 nanometer MOSFET, which is ancient history. Yeah, so this is 2000s or whatever in terms of technology development. So it's even getting worse. Yeah? Why is that happening, and what is the main cause? Why hot carriers are so critical? What is happening there? I told you this image of the electron traveling and then being bumped by the phonons, bang, bang, bang. But this is not the only thing, because when we get these pronounced high fields, despite of the phonon breaking, they're immediately accelerated again, and that because of the high field gradients. And what you get then, the electrons start to multiply in the crystal. Yeah, and there's different mechanisms. The most well known is the avalanche, where we are creating the one electron hits hits another electron out of the crystal. So it's existing and hits a pair of electron and hole pairs, which again are accelerated and start to multiply. Yeah? So it's really an avalanche going down a slide. And we call that, because it's an impact of the electron hitting the crystal, it's called impact ionization. So this starts to multiply the number of carriers, which is the reason why these, on the outskirts there, you see that also the currents are going up. Sounds okay. And there are devices where this impact ionization can really be used. So you can, as long as you have bulk crystals, it works very nicely. So you can turn on this multiplication and turn it off again. But typically it goes awfully wrong in the combination which we have here. So if it's in the crystal itself, you could have that back and forth, but it goes wrong if you are near interfaces, because then there's some secondary effects where the electrons and holes go into the oxide and influence the stability of the oxide, and then you're getting serious reliability problems. Yeah, so this is something. In some reasons, this impact ionization can be used nicely, but you should typically keep away from that, because once it starts happening, it's very damaging. Yeah? So the main problem about this is that you're creating significant reliability problems for the device. So you have to keep away from it. Yeah? Just as so that limits us.
When we are talking about focusing the electric field,
Yeah.
are we reducing the oxide length or increasing the potential?
Yeah, it's definitely a strike. If you want to term in this way, so normally you would say there's a channel length, and you could, this is limiting, but channel length is a bit disturbing, because you could say you just increase the field by making it just proportionally smaller, but the field really goes up because it's in combination with the doping profile change. Because this is really the problem. It's the combination of those effects that normally you learn, and we call that a long channel effect in MOSFET. So you learn channel length is important. What you have to understand that for about 20 years there have never been long channel FETs anymore. Everything you have used in your life is a super scaled short channel MOSFET, which has these limits. Yeah? So this is really problematic. The reason I'm talking about this is we get with decent CMOS, which we get today, we have very perfect devices, very high gain, very high current, but the voltage limitation is extremely lousy. Yeah? So you're down to 1 volt, and 1 volt is already bad, because it means that the impedances you get, just make a simple assumption. If you get 1 amp of current and 1 amp of voltage, 1 volt of voltage, divided to each other, you're getting to the impedance range of 1 ohm. Now, just as an idea, you have in your head 50 ohms as a reference impedance, or 400 ohms, or 377 from the outside world. There's some kind of mismatch. So that's why typical RF devices do something to enhance the voltage capability. Always. Yeah? So the scaling which we get from the digital world is going completely in the wrong direction. But we'll look at that. One thing, quantum has trouble, but quantum also has some nice ideas. And one idea which is particularly important for us is that we can combine semiconductors. And that is both done in the silicon germanium world as well as in the 3.5 world. Yeah? And the trick is, if we are thinking in terms of motorway, I gave you the image, there's a perfect motorway and we need carriers. And the idea is now, why produce the cars on the motorway? So why are we doping this perfectly aligned channel in order to get carriers in? That sounds a bit crazy, because you cannot really say if there are no carriers, the motorway doesn't work, but there is a trick. The trick is that you say, in any reasonable optical or electronic semiconductors, we are trying to do the doping not where we transport. We do it in other layers. And in order to do this, you have to start mixing materials. And that's what was done. It's been done for about 30 years, that we are starting to grow different layers of semiconductors on top of each other. Now, what could be a problem with that? First of all, can we grow anything on anything? What do we need to get semiconductors on top of each other? So what are requirements? So which semiconductors can we grow on which semiconductor? Any ideas? So for example, you put balls on top of each other, and we learned this is a crystal structure. So if you have a crystal structure for the lower semiconductors, what is a requirement for the upper semiconductor structure? Very simple. It should be somehow similar. So, for example, I think you know that there's different configurations for crystal growth. You can, for example, grow something in a cubic fashion or in a special crystal configuration. And if you do that, you can grow them in a crystalline fashion. Remember why we need crystals. The crystal idea is everything we said so far was based on this idea that because of the perfect alignment, at zero temperature we get perfect mobility. And this is only because the crystals are oriented perfectly in a shape, in a pattern. Yeah, so the crystal is an ideal structure, and everything which deviates from this ideal behavior kills our good performance. Yeah? So what we have to make sure, we grow crystals on top of each other which are similar. Yeah? Now, however, let's make the experiment of thought. What could happen if we put different semiconductors which meet these requirements of the crystals meeting? What could happen? Yeah? And now on the blue side you have semiconductor 2, on the yellow side you have semiconductor 1. And the idea is that for certain semiconductors which are not so manifold, we can get some good conditions. Yeah? And remember, what would I like ideally for something which is a good conducting layer? I want a small band gap. Why? Because then the effective mass is low and transport is good. And I may put another semiconductor to the side, which is the same. And just to give you the perfect example, which you all are using, this is the yellow one could be silicon and the blue one could be germanium. Yeah, so and just to remind us of the band gap. So this is 1.12 eV versus 0.67 eV. So we would like to transport in the germanium because there the mobility is definitely better. But we have to think about the band alignment. Because when we are just moving, this is now a PowerPoint engineering example, so be really careful what I'm saying. I'm just putting these two crystals together. Let's assume from a crystal story we could do that. Let's think now what would happen then. Yeah? What is combining two crystals if they are in thermal equilibrium, which is saying they are at the same temperature? That is easy because there's one fundamental story which helps us greatly, because if the temperatures are the same, then these Fermi levels, and what was the Fermi level? Let's just don't get nervous now because of a stupid name. The Fermi level was just this idea that there's an occupancy of electrons in one material. Yeah? And it's somewhere mid-gap. Yeah? And if you put them on top of each other and you are able to do that, it's not always happening, but let's assume it's happening. What has to align? This is ruling everything. That is that the Fermi level has to go as a straight line through the combined crystal. That is what's defining everything. Yeah? They have to be identical. And now the question is, how do these band edges, like the conduction band and the valence band, how do they move? The first thing is a lot of things can happen at the interface. So there can be charges and everything, so this can be really critical. But let's assume we can avoid that by doing a perfect growth for semiconductor 2 on semiconductor 1. Yeah? What would guide us then that the Fermi levels have to meet. And then this edge has to meet this edge somehow, because they have to align. And how does that happen? That's quite simple. That is that when we are now, you have to now think, yellow is the large band gap semiconductor, and blue is the small band gap semiconductor. And what is happening then is that there's apparently a difference. So if you have, like in germanium, 0.67 eV and there's 1.12 eV, so somehow they have to meet. And what is not clear, there's now the sum. It has to be in some way, but it's not clear how much is used here from this distance on the top and how much is used on the bottom. And there can be a lot of variations of that. In an ideal case, you have some more or less, let's say a couple of tenths of EV on the top and on the bottom, yeah, so that they're lining up. And this is simply the material composition which makes that, so that from the semiconductor with the bigger band gap, this is bending up to make up for the alignment. Then there's a little bit downside. So here there will be a smaller band gap going in this direction, and then there will be met and meet there again, so that we get some alignment of this. So, and one form of doing that is just to assume that the bigger semiconductor bends up with the larger band gap, and just there's no all kinds of things happening. But why could this be useful for the problem we just achieved? Yeah? There's one idea which is helpful, is that if this happens, then the Fermi level, which used to be here, is crossing this region in the other semiconductor. Yeah, so before, the Fermi level was not touching anywhere the conduction band. But if we align those, then because of this alignment here at this interface, the difference makes the conduction band dip into the Fermi level, which means that suddenly the Fermi level is above the conduction band, which is an ideal situation, which we had, if you remember what we started with. This is what we wanted, because then we have you have an occupied level. So if the Fermi level goes into the conduction band, it means you have electrons where you want them to be for conduction. Yeah. The good story, what we are achieving here, is that suddenly we're getting a nice situation. Now, it's always the question which way around I show this, but you see here, this is the conduction band of the large band gap semiconductor, and then for a small region we have carriers going in this direction because the Fermi level is above the conduction band, which means that suddenly we have created a situation where carriers want to be at that interface. They're automatically going there because they have an energy advantage of going from anywhere in the semiconductor. So anywhere where they want to go to this interface. Yeah? There's another thing which happens now, because this will happen at a relatively small scale. So we are again into quantum, so that some of the things you learned into quantum now really happen. Yeah? So within this, we call that a quantum wall or quantum channel. The idea is that the carriers will go there, but because this thing is quite small in nanometers, we are again going under this specific wavelengths of the electron, which means that there's some, so we cannot have all kinds of energies in this quantum wall, but we only can have defined energy, which is a typical characteristic of quantum. We're not really worried about this, just to mention it, because it's the same rules which apply because we made everything so small. That's happening there, but it's happening on a large scale because we are really having an interface can be on a full wafer, which is 10 centimeters long, but it's in this other direction. It's only a few nanometer an effect taking place. Yeah. And what have we now created? That's good. There's a lot of problems in doing so, but what is good? That you suddenly can, you suddenly have a 2D situation. Yeah, so you are creating carriers near one interface. The question is this useful or is this not useful? And the answer is it's very useful. Why? Because we are now fostering an effect of the quantum which we before in the MOSFET hated. Yeah? So assume the question is, where do the carriers come from? And first of all, there are no carriers because it's undoped. We have the same problem as before. But now people came to this idea, why not do the doping not in this region where we want the conduction to be good, but somewhere else. So maybe in the yellow semiconductor we now dope. Question is, why would we do that there? Yeah, that's quite simple, because normally you would say, if you think that from an energy perspective, if a carrier is here, there's nothing happening. So they are just in the wrong material. But then you remember what we talked about 15 minutes ago. There's this effect of tunneling. Yeah? So if the carriers which are doped are near this interface, then they are capable of tunneling through this energy barrier here. Well, this is energy positive, so it needs energy to transverse. But if this is thin enough, we can get carriers into this wall or well. Why could this be useful? That's very simple. We wanted to have an ideal channel, an ideal motorway. We are not doping there, so the mobility is good, as long as we can make this interface good in terms of growth. So if it's very rough or so, then we would have a problem, but if we can grow atom by atom by atom, it works very nicely. And remember, we had one technique or two techniques like MBE where we could really grow atom by atom. MOCVD works the same way. Yeah? So you can suddenly do that. And the nice thing about this tunneling is that the carriers have a preference to dip into this wall. So they want to go down there because they win energy. And they're not observing this energy barrier anymore because the wavelengths of this very thin semiconductor is the thickness of the layers is much smaller than the wavelengths of the electron. So that means the carriers can get out of this doping layer into this. And now, what is the advantage if everything goes right? You now have a motorway which is not inhibited with a lot of cars. And you're only limited by the amount of doping you can put into this particular barrier. This is the electronic version of using this. Just for everybody, this is one advantage. There's a secondary advantage which I at least would like to mention. We're using these heterostructures also in optics. That's the same effect, because in electronics we call that mobility, the capability to migrate in transport. Doping, when we think this from an optical perspective, is also not nice in the area where we want to do some optical things. So for example, if you have this idea of lasing, when you build a laser, you want a good propagation of the optical wave in a material. If you dope them, that typically creates a lot of problems. Yeah, so a laser uses the same thing, that we provide the carriers which then are going to lace in a different layer than the layer where the actual optical transport takes place. Yeah? So anything which you know from an LED or a laser works the same way, that you want to dope and provide the carriers which are then optically going down from the conduction band to the valence band for the same reason. So this structure which we just created is not just for electronics, but we also solving optical effects. Yeah? So the white LED, which our institute co-invented, works in the same way. You put the carriers not into the gallium nitride layer, but you put it into a layer adjacent. The electrons travel and then recombine in the layer which is undisturbed. So all the optical components work the same way. Yeah? What did we need to organize this? We needed thin layers, which we can build. Yeah? So it's only working because this tunneling takes place near. So this distance of the doping to the channel is a sequence 3, 4, 5 nanometers. And there's a technical requirement, because if you cannot grow this stuff nicely on top of each other, if there are disturbances in the crystal, then this will not work, because any disturbance at this interface will again shatter the mobility. Yeah, so this is very clear. If you are not growing this nicely, then this whole advantage goes away. So this is always what I would like to mention. It's a very interesting concept, which is called heterostructure. Yeah. Hetero because of adjacent or different materials. But the idea is that you have to grow this on top of each other. And it only works for so and so many materials. Yeah? So, for example, a good one which you know is gallium arsenide, and you put aluminum gallium arsenide on top, because when you do this, the crystalline, the lattice constant does not change and does not change the material. Yeah? For silicon germanium, it's already a bit problematic, because when you put too much germanium into the silicon germanium on the silicon, then it starts to tear. Yeah? Remember, I talked about this pseudomorphic rows, that we had this idea. You had balls, and you had a material which had a different ball distance on top. And if you mix the top semiconductor in a way that there's only a little bit of germanium in the silicon germanium, then it's nearly like silicon, but it's better. Yeah? And you have to decide how much of these additional material changes you can allow, that this makes a good heterostructure. So it's not something you get easily, but it's the baseline for what we are using today to improve devices. Yeah? There's also, we didn't talk about the second interface yet. So we only talked about, it's now the same idea, but so we have, this is what we just talked about on the conduction side, and here we have the same idea again. So in this case, the gallium arsenide is the smaller semiconductors, small gap. And the yellow one is now, again, the one with the higher band gap. Yeah? And here you see how it's forming. Yeah? And this structure, you could say this looks like some very crazy physics. This is why this thing is working. And the reason why I like to introduce it, this got the Nobel Prize in 2000 for enabling all this kind of electronics we're using today. So it's a Nobel Prize winning idea, which again uses some quantum ideas. What is done here? This is a structure which is now vertical. So we are not transporting anymore along this interface, but we are sending from top to bottom. And this structure, which you see there, the yellow one, they are both, in this case, n-doped, and the greenish one is a p-doping. So this is a bipolar structure. And this concept of the semiconductor heterostructure critically improves the bipolar transistor. We will come to that just as a first idea where you see this. I would like to single out one effect. So here we use for this structure we were trying to put carriers in an N layer. Yeah. In the vertical structure, we are trying to keep electrons which are here in the base. We are trying to keep them in the base. Why would the question which I have to ask you now? Why would there be a problem at all? Yeah, and that goes back to 45 minutes earlier when I said, think of the fish tank. The fish tank said if we have a carrier gradients, carriers will move away from their high concentration to the low concentration. And in this case, I would like to keep the holes, which are in the bipolar transistor are the base. I would like to keep them there. Because there's reasons why I want a high carrier concentration of the P, which we will explain later. And now for the barriers, just to think a little bit how this works. So if you go high in energy, in electron energy, this is a barrier here. So this spike represents a barrier which we can undermine by tunneling, but there's still an energy barrier. So electrons have to mount before they get down, classically. Yeah? So this is, for holes, it's just the opposite. So when you have holes, you have to think downwards. So let me remind you of the issue. Sounds a bit crazy always when I explain it. I'm always shocked how complex that is, but it's actually quite simple. When you think in holes, the activation of a hole goes down. So you want to go from the acceptor level into the valence band. So you're thinking downwards. Yeah? So you have to dope in a way that you're getting close to the valence band and downwards. Yeah? Now with this heterostructure, and I will explain this multiple times in this lecture because it's a bit crazy, you're building an additional barrier for the holes here. Why on earth would somebody invent something like that? Very simple, because I want to keep the holes in this base. And if there's an additional barrier, I can put much more doping to this base layer, which has a lot of advantages for me when I explain the bipolar transistor. But I can keep with adding this additional layer, so having a large bandgap material on top of a small bandgap material, I can keep the holes in a structure where I want them. Yeah? And this is the same idea as here. I can, here for this structure, I'm keeping the electrons automatically near an interface. Yeah? And now take the idea of water, which is a good one. If you splash water, it's very difficult to shut it down if you go from here to here. But if you have a very defined tube and you just have to shut down the tube, this is what we do mechanically do. If it's just a two-dimensional problem or a one-dimensional problem, it's much easier to cut it. So if you think this from the idea of a switch, the interruption of the carrier flow from source to drain, limited by this third dimension because of this confinement, as we say, is good. Because if you're building essentially a tube. And then the shutdown, this is what I said earlier, I can control people which are here much better than what I can compare up there in the room. Yeah, so this is the beauty of those additional layers you can build with the sequencing of semiconductors. Yeah? And the same is here true in a vertical configuration. This needs further explanation. But what I can do is that because of this diffusion effect, the P carriers do not leave the base. And to crack already the surprise, why is this so critical and critically important for this? You are using the bipolar concept to send out the waves. And if there was in a transistor, and if these carriers would go to the emitter, they would kill our amplification, because it's the control current for this transistor, for the bipolar transistor, would be way higher for a given doping if there's no limit for this with this additional barrier which you see here. Yeah? So what you get in the end again is a kind of switch, which is much more changeable than the one which you get without that hetero interface. Yeah, so it's good to limit in dimension. Reduce dimensionality is a very difficult task, but if you can do it, it serves great for the purpose. And what this enables, just to be very practical, is avoiding this leakage gives you the standoff time for this thing, that it lasts over a day. If you would try that with a different device, you would have great problems in achieving that. Yeah? And that's one of the reasons why I got the Nobel Prize, because that is this device is the most device used on this planet in terms of RF devices. It's a hetero-bipolar transistor. But I will explain it again, just to give you the first feeling why we need that. To round it up a little bit, just what are other things we need? What was happening if we didn't do two semiconductors, but if we did a metal on top of a semiconductor? That's also very achievable now. If you have here the metal on top of a semiconductor, you get similar things. Yeah? So you get a Schottky contact because the metal will adjust the conduction band at a certain tip here on the metal side, yeah? Which has the direct effect of, if you just put the metal on top of the semiconductor, that the conduction band bends up, and this is forming a diode. Why? Because there's a region between the metal and the semiconductor where the electrons are depleted. Yeah? You could say, doesn't sound right, but it's helpful because this is a useful diode, which is quite nice. You can use that especially in power electronics nicely, and it has a very practical consequence because this is full of Schottky diodes here because they are so efficient. We need them in power electronics, and we're also using them as gate contacts. Yeah? What is the other type of metal semiconductor interface we need? We already talked about this. This was the idea here, that we have to contact a channel for the source. So sometimes we simply want to put the metal on top of the semiconductor and make sure the current is really flowing in. Yeah? And in this case, this type of behavior which we have on the left is very disturbing. Yeah, so because it means that if I want to send current from the metal into the semiconductor, I'm getting a high resistance, a contact resistance. That's stupid, because a serial resistance in my current path is greatly a problem, because it reduces my current, it makes losses. Yeah? And then from this picture now you can understand why people put doping, because what you can do now, that's depicted on the right, instead of just putting the metal on top, you first dope the semiconductor and then put the metal on top, because what you're doing then, if you see it from this region, if there's automatically there would be a region which would be highly depleted, but if you put many carriers there, which is what we are doing by doping, then you bend this, it's still pinned up here, but then you make this layer so thin by doping that everything tunnels through. And when you then measure the current for the dope, for the diode, you get a typical diode behavior here, so this way. And but if you dope it to get the carriers very near the interface, you really measure an ideal ohmic contact. And the higher you dope, the lower the resistance actually is. So that's quite simple. So that's what we need there. Pooh, and it's the same as if for the Schottky. The Schottky is the same idea as here. When we are going to this here, so this is also moving upwards. And yeah, you could say in this way it's comparable. You have two ways of looking at that. Of course, that's the forward diode. This is there's two characteristics of the Schottky contact. So this is for zero bias, and if you of course if you put a potential here to this Schottky contact, then you can attract electrons again. So that at some point they're going near the interface and in, then you get an exponential behavior. And if you're increasing this distance here by putting a negative voltage, then you're making this depletion region even bigger. Yeah? So that's helpful. And then what you get as a current characteristic to be more useful, then you get a reverse current, where you can use the contact nicely. And then at some point when it's too high, it simply breaks down also. Yeah? And these Schottky diodes are very nice in power electronics, for those who have heard power electronics already, because they are just based on one carrier, so they have no recombination. So they're very fast. Yeah? And we like to use them for some FETs, which are not MOSFETs. We also like to use them as FET gate contacts, because they can be a gate contact with an extremely low capacitance, which is good for RF. Yeah. So this is maybe helpful. And now, just as an outlook before we close, what is really intriguing is always to look where we are in terms of numbers. So here, this is what I wanted to show earlier. So this is a modern MOSFET. So the metal gate here is, so this is 1.1 nanometers. So you can count the atoms there, because you see this resolution there. It's not bad imaging. This is really single atoms. So you can see an atom. Yeah? And why can we see an atom? Because we are looking at it with an electron. So it's an STM. So it's a scanning tunneling electron microscope. So we look with a much smaller wavelength than the nature, and then we can see the individual atoms. Yeah? And here there's some silicon dioxide. There's by now, as I told you, the silicon dioxide in the most present MOSFETs has been replaced by another silicon dioxide type of material, which we call high K, because it has a higher dielectric constant, which we like. And here's the metal gate, but you can really see the atoms individually. Yeah? So that's always important to remember. Maybe the difference is that something which I would like to start from is what is now a big secret of all these things is the interface design. Yeah? And for example, when we are playing with these band adjustments, moving them up and down, that is just to pronounce the importance of silicon again, because with this oxide we formed, the silicon dioxide, which we talked about last time, this is a material which is so good at this interface, so the natural oxide forming on top of the semiconductor, that you can really bend now the conduction band and the valence band up and down. Yeah, and that is why silicon is so important to us, because most of the materials, when we put an oxide or a metal on top, then we get mostly this behavior, which means that something like a Schottky contact is formed. That can be nicely for a gate contact, but it's not good for what we use in MOSFET, because this would never, if this is an oxide now, having such a situation, this doesn't really work well. But in silicon, it's not only the nice mobility we have, but this natural formation of an oxide, which is seamless. So there's no trouble at this interface, because it's a very nice interface. It's similar to what we have with the aluminum, with the natural oxide formed on top of the surface, which is stable. Yeah? So that's why. So this is a very important consequence of this material source. So this is, although I said silicon is not optimum in terms of transport properties, that is correct, but it makes, because it's so beautiful crystal, and it makes such a nice surface, that's why we use it so much. So that's really the reason why this industry is so important to us. Yeah. But because it takes a lot of time to develop that, I would like to leave that for next time and just to explain that again. But what you should take from this is that with the formation of the layers and reducing the dimensionality, as we say scientifically, you can build, you go from a water bath into a tube, which you can nicely interrupt, and where you can control by engineering, you can control where single electrons go. And you can say, well, I'm not interested in an electron flowing. Yes, but what you definitely are interested in, whether this will last till tomorrow or whether this is down by the minute. Yeah, and this is really these effects we're discussing here are making sure that this stuff is efficient, or that your microprocessor, let's see how hot it is, still, I would say close to 80 degrees by now. This makes the difference. Yeah, it's just these effects which critically affect for a given performance. So this thing should be calculating fast, or this should transport efficiently, but it should be cool. So now I leave you to your cool Coke or whatever you're going to drink now, and I hope you enjoy the holiday tomorrow, and thank you for listening.